Hi everybody, I'm Professor Rad, and in this video we are going to conduct a two-tailed hypothesis test. So first I want to review the steps for hypothesis testing, and then we'll go ahead and conduct the hypothesis test. So for our steps for hypothesis testing, I've got kind of a list going on here, and then I also have a visual presentation of the data, or of the steps rather, so you can kind of see which is going to be easier for you to reference as you go through a hypothesis test. So the first thing you want to do is make sure that you can do it. So in order to do a hypothesis test, you need either, well, first and foremost, you need a simple random sample. You need a random sampling. And then you need either your sample size to be bigger than 30 or an approximately normal distribution for your population. And these are our requirements for the central limit theorem. And so this is built off of the central limit theorem, so it makes sense we have these kinds of requirements. Next, you're going to summarize the information that's given to you. So you're going to collect your population mean, a sample mean, a standard deviation, a sample size, significance level, all that good stuff. Okay, so you're going to collect everything that's been given to you. And that's sort of our like mise en place, if you will. That's sort of our, okay, get everything in place. We got everything in place. Now let's cook the meal, if you will. So you're going to state your null and your alternate hypothesis. So remember, this is what you are contesting, and this is what you suspect. Then we're essentially going to do a forwards central limit theorem problem. So you find your z-score to the nearest hundredth as usual. You're going to draw a picture. You're going to find a p-value, and then you're going to draw your conclusion. And the drawing your conclusion happens comparing your p-value to alpha and whether you should reject or fail to reject. So when we do that forward central limit theorem problem, right, usually we find a percent or a proportion or a probability. Notice how those all start with p. Yeah, that's why it's called p-value. That's where it comes from. So that's what we're going to do. So if I want to look at a more visual breakdown of this data, it's still kind of, chart-like. But we've got our checks. Do we have our simple random sample, and do we have our sample size more than 30 or a normal population? Then we collect mu, sigma, x bar, n, and alpha. So we collect all those bits of information. And then depending on the type of test that we're going to conduct, we're going to have a different sort of perspective on this. I'm trying to get all this on screen here. So if we conduct a left-tailed test, we're going to follow these steps or these guidelines over here. If it's a right-tailed test, this will give us good guidance. And if it's a two-tailed test, like we're going to do in this video, then we'll follow these steps here on the right. Okay, so this is what I'm going to be looking at today. Then at the very end, you draw your conclusion, and we had this on a previous video when we talked about drawing conclusions for hypothesis tests. So you compare your p-value to alpha, and then you decide whether you reject or fail to reject, whether results are significant or not, and then what you can conclude. So let's go ahead and walk through our two-tailed hypothesis test example. So this says, according to colleges.com, the mean age of students attending a community college is 29 years old. Gary suspects that this might not be true of the students at MVCC. He finds an SRS of 50 students and determines that they have a mean age of 23 years old. Assuming that sigma is 6 years, conduct a two-tailed test at the O1 level to determine whether or not students at MVCC have the same mean age as at other community college students. So for our check, can we do a hypothesis test? So we've got a simple random sample of 50 students. So that's the first check. And then the second is either a sample size more than 30 or a normal population. So he found a simple random sample of 50 students. That's more than 30. So yes, we can do our hypothesis test. So then what I'm going to do, I read through just one time to kind of get a sense of the problem. Now let me highlight some information and see what information I can write down. So according to colleges.com, the mean age of students attending a community college is 29 years old. Okay, that's one bit of information. Then it says, Gary suspects that this might not be true of students at MVCC. So he suspects. Suspicion is a key for a hypothesis test. So anytime they tell me a suspicion, I'm going to highlight or box that in. He finds his simple random sample of 50 students. So SRS of 50 students. And he determines that they, meaning his sample, have a mean age of 23 years old. Assuming that sigma is 6 years, we're going to conduct a two-tailed hypothesis test. And we're going to use the O1 level. All right, so I only had 3 highlighters with me at the moment, so that's kind of why I'm repeating colors here. But I also repeated my colors a little strategically here, and I'll point out what that strategy was. So in the green, I have population information. So it says the mean age of students attending a community college is 29 years old. This is a statement about community college students in general. This is a parameter, so this is mu. Mu is 29 years old. Then they told us to assume that sigma is 6 years old. So we can just put this here, 6 years old. So what I did here was I highlighted in green the population information. Then in purple, I highlighted the sample information. So we have an SRS of 50 students. That's telling us how many people Gary looked at. So N is 50. And they, meaning the sample, have a mean age of 23 years old. So X bar is going to be 23 years old. Okay, so that's me collecting the information given to me here. And then what I have in yellow is the stuff that pertains specifically to hypothesis testing. So they told us that alpha is 0.01. So I have that over here. And alpha does not have a label to it. And then the suspicion is going to help us with the null and the alternate hypothesis. So I'm just kind of bringing, see if we can get all of this visible at once, maybe, kind of. Yeah, kind of. All right. So since this is going to be a two-tailed test, and I know that because they told us to do a two-tailed test, I'm going to follow my two-tailed test kind of guidelines over here. So let me try and fit this all here. There we go. So if they did not tell me to conduct a two-tailed test, I would still know that this was a two-tailed test because of Gary's suspicion. He suspects that this might not be true. So since his suspicion is that the claim is just not true, we don't know whether Gary thinks students at MV are older or younger than 29. He just thinks that it's not true. So our null hypothesis is going to be the claim that's being made about community college students in general. That's what we summarized as mu over here. So whatever you summarize as mu, that's going to be your null hypothesis. So I'm going to say mu is 29 years old. And because our alternate hypothesis is for a two-tailed test, that means that mu does not equal that number. So mu does not equal 29 years old. Okay, so that's us stating our hypotheses. Now we want to find our z-score. Now for a two-tailed test, because it is two-tailed, we're going to have two z-scores. We're going to have a positive and a negative. So we're going to use this formula here for our z-scores. So we're going to get z is plus or minus x bar minus mu. So x bar was 23 and mu was 29 times the square root of n. N is 50. And all of that is going to be over sigma. So sigma was 6. Now, when I type this into my calculator, don't type in the plus minus. We're just going to ignore that. That's going to be part of our answer in the end. So there it is. I was trying to find where I put my calculator. All right, so let's go ahead and punch this in. So we're going to have 23 minus 29 times the square root of 50. And then we'll divide that by 6. Now this calculator likes to keep my answer in radical form. So I've got a button here on the side that's got like this little squiggly here. And when I press that, it'll put it in decimal format for me. Holy smokes. Okay, so we have negative 7.07. Whew. So instead of negative 7.07, we're going to say plus or minus 7.07. So no matter what sign you get here, you're going to have plus or minus for a two-tailed test. So for our z-score, we're going to say plus or minus 7.07. All right, so that's finding our z-scores. Now we want to draw the picture on a standard normal curve. So when I draw the picture, I'm going to put 0 in the middle. I'm going to put a negative 7.07 on the left and a positive 7.07 on the right. And then I'm going to shade in, instead of between them now, I'm going to shade on the outside. And this is why it's called two-tailed, because you've got the two tails of the graph of the beast. Now, to figure out our p-value, we're going to look up the negative z-score on the table. Which table? Ta-da, this one. So this is what we used for our forwards and backwards problems. So we're going to use this table. And our z-score is huge. That's why I kind of reacted the way I did when I saw it. So I'm going to look up a negative 7.07, which on this table is less than negative 3.7. So we're going to use 0.0001. Now, I did have a typo on this. Well, not typo, but left out a piece of info that's helpful. So over here where it says look up z-score on table, you want to look up the negative z-score on the table. Because what this is telling us is that this is 0.0001 to the left. And because our curve is symmetric, it's 0.0001 on the right as well. That's why our p-value is going to be 2 times that value from the table. So our p-value is going to be 2 times 0.0001, which is just 0.0002. Whew, okay, so now let's draw our conclusion. So to draw the conclusion, we're going to compare this p-value we just found to alpha. And I'm going to write this out over here. We're going to compare the p-value to alpha. Our p-value is 0.302, and alpha was 0.01. So if I compare them, we've got a 0 and a 0, and then a 0 and a 1. So 1 is bigger, so that means that alpha is bigger than our p-value. So when I look at how I draw my conclusion, we're in this first situation where the p-value is less than alpha. So this means we're going to reject the null hypothesis because the results are statistically significant at this level. So since we reject the null, we conclude H1. So let's summarize our findings here. We are going to reject the null hypothesis. Since the results are statistically significant, at the O1 level, we're able to conclude what H1 said. So mathematically, this is an equation, or kind of a non-equation really, that mu is not 29. But what did mu stand for? In the context of this problem, Gary is suspecting that students at MVCC are not the same age as community college students in general. So this statement that mu is not 29 years old, in terms of context of this question, it means the mean age of students at MVCC is not the same as the mean age of students from other community colleges, or community colleges in general. So that's what he can conclude, since the alternate hypothesis won. So we are able to conclude that the mean age of students at MVCC is different from that of community college students in general. All right, so there we go. We've just conducted our first hypothesis test. In the next video, we will conduct a left-tailed hypothesis test, and we'll follow the similar guidelines. So I'm looking forward to seeing you then. In the meantime, have an excellent day. Bye for now, everybody.